Each check. Now on to the content. So we're talking about different types of prisms and then Cartesian products, and it's really just the same idea on and on and on. In this unit, it's just multiplication. So what are the different ways in which we could multiply? It seems like there's more and more ways for me to invent complicated applications of multiplication, but really it's how it's always been. Same thing with addition, subtraction. The idea being that we want to be able to kind of hit this concept from all different angles. In a simple example, something that I experienced personally is that at a young age, I knew that if I wanted to figure out the amount of tax, for example, that could be applied when you purchase an item, or the discount, I knew that if it was 8% sales tax, that I multiplied by 1.08. But at first, I had no idea why. And in a lot of ways, it's something that becomes second nature. You take it for granted. You don't always explore. What was the reason for that? Sometimes something just works. You just do it, right? But there is a thinking that goes into why those things work the way they do. So that's kind of what we're trying to get at. Because the last thing you want to tell your students, short of them, coaching them to get problems right on the test, which happens, but that hopefully that's not the point of learning. The point of learning is for them to understand the material. Short of that kind of thing, you really want to kind of dive into the rationale behind certain concepts. So we'll talk about that among other things. Right. So, but the prism is just an object that's projected out into 3 dimensions. All right. So you have a base area. In the case of I'll go simple first. We'll just focus on this guy here, the rectangular prism. We're talking about a base, and any of the sides, and that's a kind of a misconception. The side that it sits on does not necessarily have to be the base. It's just whatever side that is the side that's being projected out into 3 dimensions. All right. In the case of a rectangular prism, it could be any of the sides. In the case of this one that looks like a bar of soap here, it's based off an ellipse. That front face is going to be the base, because that's what's being projected out into 3 dimensions. Let me get my geometry tool going here. All right, so and let me get rid of the arrow. Now that I'm thinking about it, anything that I highlight here is necessarily going to be the base, so I don't think I need to label each of them. All right. So, for example, when you're looking at the triangular prisms, you might look at it and say, well, it's sitting on the, like that rectangular side. It's kind of like a little wedge, but it's the front side that's actually the base, because that's the one that's projected out into 3 dimensions. And what I'm talking about is, when I say projected out into 3 dimensions, if you take all the points that make up your figure and extrude it with the same height in the same direction, that's a projection into 3 dimensions, right? And that, the last one that I just diagrammed there, that bottom left-hand point, it's a little trickier to see because it's going, behind the object, but it's still there, And so that's happening when I'm dealing with the rectangular prism. That's a little easier to see. I got 4 points and a consistent quote unquote height, because it doesn't feel like a height, but it is, because once you establish where the base is, the height is going to be orthogonal to that, or in another world, we could say perpendicular to that. All right. So those are some ideas that can kind of come into play. Now, it's a little bit more difficult to see depending on how complicated the figure is. So for example, that ellipse, okay, well, where are the points that I'm gonna shoot out into 3 dimensions? Well, you'd have to have a little bit of experience with conic sections. So some of this you're just gonna have to take my word for, but I can tell you that when you have a conic section, and this is definitely way beyond what an elementary class would be interested in, but you should be interested in it because you want to be the source of some of the knowledge in the class. You know, you don't want to have to Google everything. So if I can get my my line draw tool to work properly, oh, there we go. So what you have are 2 axes that make up your ellipse. One of them's longer than the other. Right? The longer one is called the major axis. The shorter one is called the minor axis, and they always form a perpendicular at one another. Right? Where they intersect on the ellipse, those make up the vertices of the ellipse. All right, so these are the vertices. So I'll just go with the singular, because once I identify one of them as being a vertex, the other ones are going to be vertexes or vertices also. All right, so that would be each one of these points. So I'll highlight, maybe, yeah, I think I'll just highlight them. Oh, that looks terrible. How about no? So this point, this one, and this one. Those are all our vertices. All right. So it's those points that are projected out into 3 dimensions. All right. Harder to see in some cases than others, but it's all there. All right. So, you know, you think about applications of these things, you know, when a student asks, like, why on earth would I need to know about an ellipse? You can talk about things like orbits, just general constructions of different figures. Like, you know, a football is elliptical in nature. I mean, it's not this particular figure, but it's similar conceptually. You know, it's got a cross section that's an ellipse. So, you know, there's things in their lives that they could look at and say, oh yeah, I've seen that before. You know, same idea with this figure, which is a cylinder. Again, you have the base area. It follows the same rules as an ellipse. This is a perspective drawing. This is supposed to be a circular base, but the points are always going to be the most important points that you project outward from are always going to be along the major and minor axes. In the case of a circle, it would be the radius or radii. All right, so we project upward from this guy, from this one, from this one. And I'll do this one in a different color so it stands out and pops a little bit. All right, and so that ends up being the projection outward. And then you can see, you know, I mean, with the hexagon, for some reason I have 2 rectangular prisms. I don't know why. I don't need a second one. The triangle I think is a little easier to see, but then we have the funky pentagons and so on. You know, so when I talk about this triangular one, it's pretty easy to see, but you know, you might take a second and really think about when you're looking at something like the Pentagon or that funky shaped object, you know, like really what's going on there, you know. So for this one, well, this one, which one am I talking about? This one that I'm marking up in the lower right-hand corner, you see you get all these little points along the way because it's some just funky shape. Every one of those interesting points there is getting projected out into the 3rd dimension. So we don't have a structure that we can rely on, like in the case of an ellipse or a circle or other, you know, familiar geometric figures. This is probably something that was hand drawn or constructed just using, you know, arbitrary points. And all those points would need to be then projected out into the 3rd dimension. All right, so it's, in terms of coming up with the diagram, it's a little bit kind of more trouble than it's worth, but I do want to get the point across. All right, so all those points get projected up to give you the outline of the upper surface, which is a little divot in there, and it's happening behind the scenes, and so that's where you get the top. All right, so there's a lot of funkiness going on, and same idea with the well, actually to a lesser extent, the pentagon and the hexagon. They do get more complicated because they have more points, but not anywhere near what I just did with that other funky shape. Okay, so we're looking at so there's my pentagon. Now again, I'm just extruding out into that third dimension. And that's actually going to be the foundation of the tech assignment. So, and I'll take this one as a typo. This one really shouldn't be. This is a repeat performance. We already got this guy. So somebody wants to submit that for typo bonus by all means. All right, so let me just crank out this one. So this would be my base area. Oh, I didn't go all the way back to the starting point. That's why I didn't create the polygon. You'll see that come up in the tech assignment also. All right, so all of these points get extruded out. Keep using that word over and over again because that's the terminology that's used in GeoGebra. But all it really means is that you're projecting out into the third dimension. All right, so pretty reasonable. Just checking that real quick. All right, so Cartesian products. Sometimes I don't know. Like I mean, a lot of the terminology that I'm using here I get from the textbook, and just different research and such, and so it's kind of tricky because I'm trying to sort of balance like what the appropriate terminology is with something that ends up being a fairly simple concept, and so I don't want people to think that I'm trying to incorporate big language here for the sake of incorporating complicated terminology. And it's really not like that. So Cartesian products, well, there's a lot going on there. First and foremost is the name. You're like, oh, what the hell is this? Cartesian, anytime you see that, that is a derivative of the last name Descartes. So Rene, I thought it might be one N. I'm not sure. Descartes. I'm just going to look it up real quick because usually the masculine in French, en français, is spelled a particular way. Yeah, it's the two E's for the feminine, but I just want to make sure. Yeah. And of course, the accent aigu. All right, so it's the cart part of Descartes. That gives us the Cartesian component. All right, so that's fun fact of the day, I guess. Although, I kind of like throwing a little stuff like that on skills assessments only because it's like, your students will benefit from that. Do they need to know that in order to answer questions effectively on an assessment? Probably not. But having a little bit of, trivia knowledge related to math, it's probably not a bad idea. It starts the conversation a little bit, whenever I talk about sequences, I always talk about Carl Friedrich Gauss, who's a very famous mathematician and also a big name in science. So his whole thing was, when it comes to sequences, is that he came up with shortcuts for finding the sums of large numbers of values. So if you think, for example, like I want to add up the numbers from 1 to 5, 1 plus 2 plus 3 plus 4 plus 5. That's not difficult. You just write it down and you get to work on it. But in an elementary class, Carl Friedrich Gauss was told or asked by his teacher, because he was finishing his work too quickly, to add the numbers from 1 to 100. And so he's like, all right, I'm game. Comes back a couple minutes later, having already done it. And the teacher's like, you did that way too quickly. You must have cheated. And the student showed his solution, and it was novel. It was the kind of thing where it's like, that's interesting. And I kind of feel obligated to show it now. But yeah, so what this student did was he took the number, so the sum from 1 to 100. So the thought was that this would take the student a while. He'd say, okay, well, what's 1 plus 2? That's 3, plus another 3, that's 6, plus 4, that's 10. Oh, it's going to take a while, But what he did was he said, okay, I got the number 1, 2, 3, 4. Start counting them out. That, all the way up to 50. And then what I'll do is I'll just, I'll make this a little easier on myself. Instead of adding 1 plus 2 plus 3 plus 4 all the way up to 50 and then doing it from 51 to 100, he said, let me see what would happen if I added 1 and 100. All right. And so he got a result. When he added those values, he got a result of 101. So then he said, okay, well, let me take a 99 and add that to the 2. Also 101. Same thing with a 98. A sum of 101. 97, ... 51. Every pair of values gave a sum of 101. So he said, okay, well, how many pairs do I have? All right. So he said, all right, I got 50 pairs that add to 101. So all I'd have to do is find the product, multiplication as a shortcut for addition. I'm talking about that. 50 times 101 is 5,050. All right. So that's the contribution, and he generalized it. He created formulas from it. But this is the method produced by Carl Friedrich Gauss. And I think in the days of Common Core and the days of next gen mathematics and like No Child Left Behind, Race to the Top, anything, whatever buzz phrase you can think of, all this, the history kind of gets lost, but there's interesting stories in there. And you think about your favorite history teacher, and that the teacher that you loved from history class, because we don't all, not all of us love history. That was not my favorite class, but I do have a favorite history teacher, and that history teacher made everything into a story. And if you like history, it's probably the storytelling components of it. I guess there's some people out there that probably love memorizing facts and knowing that information, but I would say in most cases it's the stories. There's a history there. So do you need to know this information in order to be successful in math? Of course not. But it's nice to know, and it's nice for you to be a storyteller in your math class every now and then, and encourage your students to be storytellers too. So that was a quick aside. I figured I'd talk to you about that because, you know, some people know that story and a lot of people don't. So I figured it was worth bringing up. But Rene Descartes, his contributions were, you know, anytime you're creating a graph on graph paper with X, Y axes, you know, plotting a point, 2, 3, 5, 7, something like that, you're plotting those on a Cartesian plane, right? So first coined by Rene Descartes. So, well, anyway, in general, the set consisting of all possible ways of pairing elements of the set A with elements of another set B is called a Cartesian product. Right? So if you think about X and Y values, so you think about, you know, like you're plotting points on a graph. And I could do that really quickly just so you have it. So, and I'll just kind of chuck that in here. So let's say you wanted to plot the point 1, 2. So that XY axis is the Cartesian plane. All right. And actually, let me move that down a little bit. Positive value. So 1, 2 would be plotted here. So here's 1, and there's 2. That's my coordinate in the Cartesian plane. And so I'll kind of make it into a little bit of a more like a question, but so I'll say plot 1, 1, 2. Right. So that's the example. That's a Cartesian plot. Right. What a Cartesian product is telling us to do is take those numbers that you have in your ordered pair, and instead of just plotting them, multiply them. Right. So with that in mind, I could have Cartesian addition. I could have Cartesian exponents. I could have Cartesian whatever you want. Right. So that's why I'm saying, like, some of these terms, they're unnecessarily fancy, but they are rooted in something that's meaningful. Right. All this is saying is that you have an ordered pair that's coming, you know, if you look at the example that follows, it's coming from a table. You're pairing values. And from that, what are we doing? We're going to multiply. We're going to add them. We're going to subtract them. We're going to divide them. You know, that's all the operation associated with the Cartesian relationship. All right. And again, this is more for your knowledge, general knowledge, than it is for you to, you know, wow your students, because they're going to be, the eyes will glaze over pretty quickly if you start going down this rabbit hole too quickly and too long. But it is worth kind of giving them a little bit of a taste of the history behind it. All right. So the example here, the license plate of a very small state consists of a letter following by a single digit number. All right. The reason why I make the statement that it's of a very small state is because if it's a letter followed by a single digit number, you're only going to have so many license plates. Right? Can you imagine? You see on the highway, you see the car speeding down the road. Oh, what's the license plate on that car? T7. You tell the cop when they ask you what the license plate, you get the number, you get the license number on that license plate number on that car. You say T7. You're gonna be like, I think you might be missing a few values there, and that's because it's not just a pairing of values. But let's say it's a really small state, really small, like 13 colonies small, and like somehow they have cars with license plates. Anyway, so how many distinct license plates of this description are possible? Well, one way to do it is to create what we call a sample space, right? This distribution, if you have any experience with statistics, these terms might be familiar, but this is called a sample space. I cannot make my squiggly brackets tonight for some reason. Sample space. And all that is a listing of all the possible outcomes that you can have. So all we're doing is we're taking the letter A and assigning to it each of the digits from 0 to 9, doing the same thing with B, with C, with D, with E, with F, and all the way down to Z, right? But when you think about New York State license plates, I don't know what the numbering convention is, but typically what I see when I look at license plates, unless they're the vanity plates or special plates for cops or for what do you call it, the UN people, dignitaries, it's typically 3 letters followed by 4 numbers. Right, so it kind of that gets pretty large pretty quickly. I would not want to make a table out of that information, right? But from this, we can see that there would be 260 possible outcomes, because I would take the 26 letters in the alphabet and multiply it by the 10 digits between 0 and 9. And it's as simple as that, right? That's how we get that information, by taking the total quantity associated with each variable, all right? So let me highlight that. Yeah, I'll do yellow. So there's 26 of these. And there's 10 of these. Yeah. So in a way, it's like finding the area, because you're finding the dimensions. How many rows, how many columns, multiply them together. Right. Now, if you need to know the specific outcomes, it's a little bit of a different story, right? Because you could create it in the form of a table, but you could also create it in the form of a tree diagram. Now, a table with 260 values, you can see how using the dot dot that can streamline it, because once you get a sense of the trend, if you're displaying the relationship, it's pretty easy to kind of inform your reader based off of the structure of the table. But when it comes to tree diagrams, it's a lot more challenging. So we tend to work with only tree diagrams when we're dealing with small sets. Right. So the case of 2 pairs of shorts and 3 t-shirts. All right. So what we do is we start off, you go into the dresser and you look and you say, okay, I got 2 pairs of shorts. Which one am I going to go with? S1 or S2? And once I decide which one it's going to be, then I have another choice to make. And that's going to be t-shirt 1, 2, or 3. Right. So that this would be a way of listing the outcomes by creating a tree diagram. But then we could also go the route of creating the sample space, the listing of all possible outcomes. Right. What multiplication helps us do is determine how many there will be in the total number of outcomes without having to list them all out. Right. But sometimes there is value in knowing what those outcomes are, especially if we were talking about the idea of like matching, the style of t-shirt with the style of shorts. I mean, some colors clash, right? And so when that happens, you would eliminate some possibilities, right? So, you would have an idea of what the total outcomes would be. Yeah, sure, the total number, but you'd also like to know what those outcomes are so that you can look through it and say, well, that pairing doesn't make sense, that one doesn't make sense, and so on. All right. So that's an example of how Cartesian products can be useful, because if you know how many there are of one variable and how many there are of another variable, you multiply them together and you have the total number of possible outcomes. All right. So the exploration here talks about the prisms. So we want to find the volume of a prism that's 1 foot long with a right triangular base. All right. So it's very important, and this is what I was talking about on the previous page, that you're able to identify which side is the base. Well, the key here is that it said right triangular, right? So at first glance, we tend to think that whatever the object is sitting on is going to be the base, but that's not the case. I'm rotating a smidge. All right. Again, we want to have consistent extrusion into the 3rd dimension. So whatever side has that relationship is the side that you're going to call the base, right? So in this case, the face is the base. All right. So that side there is going to be the base. Now they tell us the dimensions, the three sides of this base. I'm sorry, yeah, three sides. I don't even know why I questioned myself. Three sides of the base are 3, 4, and 5. All right, so what I'll do is I'm just going to pull out that triangle because sometimes these diagrams get a little messy. So I'm going to pull out the triangle and look at that separately. Undo. And the amount of time it takes to do this, I could have just redrawn the triangle. So I got a right triangle here. The dimensions are 3, 4, 5. So in a triangle, we know that the longest side is the hypotenuse, right? And that side is going to be opposite the 90-degree angle. So that's the hypotenuse, right? And you might look at this and say, wait, we're going to be in elementary school. You're dang right it is. But I didn't learn that until 7th grade. Well, that was true for me. The 7th grade, let's see, that's 13-ish, back in 1991. A lot of things have changed since then. Right? And so among some of the more benign things is the fact that, right triangle exploration is now an elementary school topic, as it should be. Yeah, I remember, and this is like a completely unrelatable example for many people, because when you look at my shelf behind me and you see these starships from Star Trek, some people look at that and say, "Oh, cool, you got models, model ships behind you." Some people are like, "Oh, cool, that's a Starship Enterprise," and some other people are like, "What the hell is this guy talking about?" So there's a nice mixed bag of that. But yeah, I remember in one episode, and this is back in the early 90s, they were talking, and it was a kid who was an elementary school student, and he said, I got to go. I'm late for calculus class. And because the show takes place in the 24th century. And so I looked at that and I said, yeah, that makes sense. 24th century. Hundreds of years from now, yeah, we better advance as a society. We better advance to the point where people can take calculus, maybe not in elementary school, but at a younger age than they're currently taking it. Otherwise, what are we doing? So when they started doing multiplication in first and second grade, simple multiplication, but and really not in the sense of that they're asked to do the multiplication algorithm, but really just kind of the idea, like laying the groundwork for the ability to multiply. That makes all the sense in the world to me. But there are some folks, and when you're teaching your own class, you'll experience this, that they kind of get stuck in the past, and it's really not in the past in the sense that they love the way things were. It's more that they love being familiar with things. They want things to be the way they are familiar with them, and so we gotta move past that, because how do we advance as a society? And math is one of those important areas, math and science, that if we want to advance as a society, when the best and the brightest get to an age where they're the most productive in society, when they hit their intellectual prime, just like an athlete. When the athlete hits their physical prime, that's when they get their most production. For an athlete, they want to have that number of years be the widest margin as possible. So why would it be any different intellectually? Right? Why would I want it to be that a person has to get to the age of 30 before they're qualified to really make significant advances in the realms of math and science? We got to get there sooner. I want them to do that. I want them to do it in their teens, but I'll settle for in their 20s. So this kind of thing, like there's no reason to shy away from it, and very often when there's a curriculum change, the resistance is these kids can't do that. There's no way they'll be able to understand that. Well, you don't know until you try, so give it a shot. All right, so 3 sides of a triangle, 3, 4, 5. So 3, 4, 5. Doesn't matter where the 3 or 4 go. I know the hypotenuse has got to be the 5. All right, all well and good. I need the volume of that prism. Now, they said it's 1 foot long. All right, so that's implying that the extrusion is 1 foot into the 3rd dimension. So this would be 1 foot. All right, so we know, talked about this last time, and it'll come up again when we talk about the tech assignment, that the volume is equal to the base area multiplied by the length of the extrusion, or the height. All right, so something that's very important that gets lost very easily, when they say 1 foot long, you're going to have a battle when it comes to language, because, and I don't mean necessarily like English language learners. That's always a concern, consideration, I should say. Concern works too, but consideration is probably more appropriate. Because the English language is hard. You've seen my grammar, and I grew up in the system. I'm supposed to know this stuff, but it's just dreadful. So I know that there are like people that are learning it for the first time. It's like like if you're able to pick up this language, then you're smarter than I am. I'll tell you that. So that aside, people get fixated on keywords, and I mentioned this before, and I'm going to keep emphasizing it. The fixation is something that you have to, like one of the buzzwords now is flexibility. It really matters when it comes to the language of a word problem, that students develop fluency and flexibility in terms of the terminology. So what that means is when I say base area times height as a general rule, you will have students that say, wait, it says 1 foot long. Long means length. Length and height are 2 different things. Not necessarily. Depends on the context. So length, if I can spell, height, and depth all play the same role when it comes to 3-dimensional figures. So we say, just as a shorthand way of saying it, volume is equal to base area. I said area accidentally. Base area times height. That's the shorthand way of saying it. That's the tried and true. V equals A, capital A times H, but it's interchangeable with length and depth, right? And so re-emphasizing that and reinforcing that in class is very important, right? So I need the base area. I got the height. That's going to be equal to 1. Now, you got to be careful because the units here, right? So we'll get into that now. The units here are inches. We want to have consistent units, right? So that's pretty easy, for an adult or an older kid to look at and say, well, 1 foot is equal to 12 inches. But if this is the first time that they're seeing unit conversions, that's a lot to spring on people. You're like, okay, wait, hold on. I got to keep track of base area times height, meaning the same thing as base area times length, meaning the same thing as base area times depth. All right, I got that. That's fine. Wait, now I got to worry about units too? What are you doing to me here? So it's something that you want to build towards, right? So there should be conversations along the way where, okay, simple worksheet, multiply 12 inches times 2 feet. What do you get? And and let that be the subject of the worksheet. You know, that's that activity for the day. And let them get a few wrong. You know, and you know, one of my colleagues says, whenever she's teaching a class, she says, give me a wrong answer. You know, like she asks a question and she says, give me a wrong answer. And then, you know, she makes a big show of it when they accidentally give or actually give her the right answer. Because I asked you for the wrong answer. What are you doing giving me the right answer? I asked you for the wrong answer. You know, the whole point behind it is so that you can kind of manufacture a learning experience, right? So the good wrong answer here would be if I were to say, what is 12 inches times 2 feet? If a student says 24, I say, give me a wrong answer. They say 24. And I say, great wrong answer. Why is it wrong? They may not know. All right. My follow-up there would be, what are the units? Is it inches or feet? And they'd say, I don't know. And be like, you're dang right, you don't know. Why don't you know? Because you use 2 different sets of units in your product. Right? If you used only one set of units, then you would know exactly what the right answer is. But because you use 2 different sets of units, now you have confusion. Right? So when I go to find the base area here, so area is equal to length times width, base times height. So now I'm using height again, so the context gets a little out of hand. But I could say length times width. I could say it any way I want, but it's the product of the 2 dimensions. All right. And that's something that you want to consistently get across to your students. All right. The area is, yeah, it's base times height. But it's also length times width. You could look at it as leg times leg. Because in a right triangle, you have 2 legs and a hypotenuse. All right. I'm sorry, this is a triangle. It's half of all those. Right? So those are all different ways that you can say it. And that's part of the conversation. In the class, you would say, all right, what's the formula for area? Half the base times the height. Okay. What's another way I could say that? Half the length times the width? Yeah. Half of this one times that one. Beautiful. How did we know it wasn't the 5? It's not the base and it's not the height. You know, those are all the conversations that I encourage you to have with your students. So 1/2 times 3 times 4. That's going to be 12 times a half, or half of 12 is 6. All right. Now the units. This was 3 inches against 4 inches. And the 1/2 is just a scalar, right? It's just a multiplier, right? So what I have here is inches multiplied by inches, right? If I take 2 values and multiply them by each other, like if I said, what's 5 times 5, you'd say 25, probably. You could also say 5 to the 2nd power, right? If I said x times x, you probably come back with x squared, right? It's the same idea here. If I say inches times inches, so let me go with the other notation for this. Instead of saying, you know, instead of using the quote approach, I could say 1/2 times 3 inches times 3 inches. 4 inches. I get my 6, but inches times inches is going to be inches squared. So that's a nice little conversation, again, that you could have with your students and say, well, where do you suppose these units are coming from? And I would say, well, what do you get when you multiply? I would use the same example, just what I said. What do you get when I multiply 5 times 5? 25. What's another way to write that? 5 squared. You know, and there you go. But again, there's a lot to spring on them, so you want to build towards that. Writing repeated multiplication as exponentials, as powers. So I would have an entire day or worksheet or both where we're just exploring different ways of writing numbers that are repeatedly multiplied against each other. So I would say rewrite 2 times 2 times 2 times 3 times 3 times 3. And then hopefully they come back with 2 to the third power times 3 to the third power. Right? But you work towards that. So you have your base area 6 inches squared, and your height, instead of 1 foot, we're going to say 12 inches. All right, so I got 6 inches squared. I could even take the whole thing and highlight it. So inches squared times inches is going to give me inches cubed. So 72 inches cubed. All right, could have figured that out a lot quicker, but again, our goal here is not to just do the math, it's to learn how to best explain it. And getting into those conversations is really a helpful approach. Now, I know that there are plenty of people out there that are going to just want the step-by-step approach. And that's fine. You know, like, what do I do first? What do I do second? What do I do third? Is that all I have to do? Okay, good. That's all wonderful stuff. You got to make them work for that. You got to make them earn that step-by-step. The thinking comes first, the process, the conversations, and then with the promise that, hey, listen, I'll give you the step-by-step. I'll give you that. I'll give you that on Tuesday. You know, like it's on Monday, or we're talking on Monday. I'll give it to you at the end of class on Tuesday. But for now, just try doing it my way, and let's see where we get with it. You know, at least kind of make them jump through those hoops, so that if they're going to get that deep understanding, it's more likely to happen in that fashion. All right. Number 2, suppose license plates consist of a letter followed by 2 digits. List 1 license plate meeting this description. That's pretty easy, super easy, fairly inconvenient. So we have 1 letter. So the letter M, followed by 2 digits, 3, 2. How many license plates meeting this description start with the letter A? It's a little trickier of a question. And then, you know, what is the total number of license plates? So 2 digits. Now you got to think about how many 2-digit numbers there are. You know, there's a statistical way, a probability way of handling this. I don't want to go down that road because that's, you know, I mean, like I said, the Star Trek in the Star Trek analogy, yeah, we'll be teaching in the 24th century. We'll be teaching our students in elementary school calculus, but we're not going to teach them statistics, you know, and calculus and everything like that right now. We have to have a way that they can relate to, right? So you say, okay, give me a 2-digit number, and they say 17, and then you say, give me another one, and then you say 32, and then you say, give me another one, and they say 45, and then you say, okay, you seem to have it, but what about one that starts with the number 0? And then they give you that look. I don't know what you're asking, but I'm going to go for it. 0, 4. Because they're just looking at it and saying, well, it's got to start with a 0 and it's got to be 2 digits. So what else can I do? 0, 4. And so I'd say, all right, we're good there. So we got some possibilities. We got 0, 4. We got 17. We got 32. We got 45, etc. All right. So then I would talk to them about that number 0, 4. And I'd say, well, that number 0, 4, how else can I say that number? And then they'll say 4. Then I'll say, that's great. Might call them a nice name like Ace. I got a kick out of that when my pre-calc teacher in high school called me Ace that one time. Felt like $1 million. You know, say something nice. Like, oh, great observation. That's why you're the man, you know, or anything, you know, whatever you can think. And so you get to that point, And then now it kind of opens things up. You ask the students, well, how many 2-digit numbers are there? And then some of them are going to say, okay, well, if I start off with the number 10 and I get to 99, it's like 90 values. And I said, well, what about the 04? Isn't that a 2-digit number? Say, oh yeah, okay, hold on. And then they would ask, well, does 00 count? And I'd say, well, yeah, sure, it's got 2 digits, right? So in the end, we're talking about anything from 00 through 99. All right, that's 100 values. All right, and it's a good connection to the powers of 10, because when you talk about, we talked about it on the previous page, if you have the number 0 to 9, that's 10 values, right? And that's in the ones place. Now we're in the tens places. So 00 to 99, now we're up to 100. Then we go to the hundreds. So 000 to 999, that's 1,000 values. So you can start talking about a relationship between, you know, the number of digits and how many there are or how many exist. All right. So then what I would look at here is I'd say, okay, well, if it's going to start with A, then I could have A00 through A99. That's 100 values. So then I'd look at it and say, okay, well, if I want the total number of possible license plates accounting for anything from A to Z, I just have to take that and multiply it by 26. All right. So I would say from A to Z, 26 values, 00 to 99, 100 values, 26 times 100, 2,600 or 2,600 possible values. Now, some of the students are going to just kind of look at it and be like, oh yeah, of course. And some of them will be like, oh, what? You know, but it's building towards that understanding that we're working for here, right? So once you make that relationship, then it's easier to see. So at this point, what I would do, because this exploration is kind of like a building process based off of what we talked about on the previous page. So when it was, you know, it just kind of off on the side, I'm a big fan of off on the side. Side examples. So we had a letter, one letter, and one number. We got 26 multiplied by 10, giving us 260. All right. Then what we just did was one letter, two numbers, or 2 digits if you want. You want to keep consistent with the language. That was 26 times 10 times 100, 2,600. All right. So we're kind of building towards something here. In theory, we're building towards a deeper level of understanding of multiplication and how it kind of plays out in terms of determining number of outcomes in a set of data. But more importantly, they're learning how to critically think and analyze situations. All right. So one letter and 2 numbers, yeah, in the grand scheme of things, do I care about that? Probably not. But having the students develop an approach that allows them to synthesize solutions given a set of criteria, that's really what we're after. All right. So next up, we're looking at 3 letters followed by 3 digits. All right. Well, we know what happens when I go from one number to 2 numbers. That got me from 10 to 100. So it's not much of a stretch to say that 3 numbers or 3 digits would get me to 1,000. The only thing we'd have to figure out is what would happen if I wanted to have 3 letters. All right. So I'll write this one, the side work here, I'll write it as 1 letter followed by 3 numbers. Right. So that's 26 multiplied by 1,000. That would give you 26,000. Right. But that's kind of the answer to a different question, but it does show the progression. All right. So now what if I wanted to say is, or what I wanted to say is 3 letters. All right. So let's kind of go back to scratch here and say, let's just focus on the letters. If I have 1 letter, we'd have 26 outcomes. So I'd look at, okay, well, what happens if I have 2 letters? You got to kind of play it out logically. And that's where the Cartesian pairing comes into play, or Cartesian products. Because what I'd look at is I would say, I'll just draw a fragment of the table that was produced on the previous page. We'd have the letters A, B, C, all the way to Z. And then the letters A, B, C, all the way to Z. All right, so our strategy was to say, all right, well, one thing that we could do is we could pair them all up and say, okay, I got AA, AB, AC, all the way up to AZ, and then go on from there. But we learned on the previous page that all we'd have to do is take the total number of outcomes for the first variable and multiply it by the total number of outcomes for the second variable. I'm going to just reduce this down a little bit. All right. And so when I do that, it's looking like 26 multiplied by 26, 576. I believe so. 676. 676 outcomes. So definitely don't want to draw out that table. All right. So if I had 2 letters, I'd have 26 by 26. 1 letter, just a single 26. So it's not too much of a stretch to say that if I have 3 letters, that would be 26 by 26 by 26. Which gives you 17,576. All right. So that's how many different ways that you could have 3 letters in your license plate. We'd also have to account for 3 numbers. So 3 numbers. That was 10 times 10 times 10. And that gave us 1,000. And so we'd get to our total number of license plates here. There's going to be that 17,576 with 4 zeros at the end. So 175,760,000 different possible license plates that you could have. That's extraordinary. But we do want to get them to the point where they could generalize this. So you kind of look at it and say, well, wait a minute. What if we didn't just multiply repeatedly? What if we used a different approach? right? So that other approach could be something as simple as employing powers, right? So this is the same as saying 26 to the third power, and this one is the same as saying 10 to the third power. So this one, this final answer, is the same as saying 26 to the third power times 10 to the third power. All right, so now you have, instead of, just a one-off situation where it's like, okay, I got the answer to one question. Now I can get the answer to every question that has a similar structure. All right, just because we discovered this relationship. All right. Now, depending on the class, the population, the grade, all that good stuff, you might want to keep the numbers a little smaller, a little bit more manageable. Instead of going with the entire alphabet, maybe you just give them the set of vowels, right? You just tell them, okay, you're only working with the letters A, E, I, O, and U, and forget about the sometimes Y, right? So this is the sometimes not part of sometimes Y, right? And in that case, now the numbers are a lot more manageable and they're even cleaner. So you can play around with the scenario. Maybe you don't want to work with letters and digits. Maybe you want to work with objects, all right? So a student is, arranging the different toys that are available, and he has 10. I'll stay with the 10 because powers of 10 are nice to work with. 10 building blocks and 4 crayons, and then you kind of work it out that way. Now, the second part of this gets a little spicier, and this is more of a challenge problem, but suppose Tennessee deletes 38 three-letter words from use on license plates. How many license plates are now available in Tennessee? All right, so 38 three-letter words. Now, you got to account for the fact that that part of the product is not going to be available anymore. So what we would do here is figure out the number of three-letter words and then multiply that by the corresponding values of the digits, right? So how many three-letter words are there? Now, under normal circumstances, we'd have to figure that out, but here they just gave it to us. They said it's 38 of them. Now, we know that for each three-letter word, there are 10 to the third possible digits. So so basically we're kind of creating a ratio, all right? And so that's another application of multiplication. And we'll talk more about that, we'll formally discuss that. But for now, it's basically saying, okay, well, if 38 corresponds to, 1 corresponds to 10 to the third possible digits, what does 38 correspond to? They look at it and say, well, how did I get from a 1 to 38? I multiplied by 38. It looks like a 0.38. So how would I get to this result? I do the same thing. I'd multiply by 38. So it starts getting at the idea that we're looking at a proportion, right? So if I tell you that one student gets 5 candy bars, how many candy bars will 38 students get? Then the student should come back eventually. You might have to coax it out of them, but they should eventually come back with the idea of multiplying. This is no different, just the numbers are a lot bigger. So our final answer here, well, part of it anyway, is going to involve taking 38 and multiplying it by 10 to the third power, which is going to be 38,000. All right. So these are the ones that are being removed. So we would then subtract that from the 175 or so million. So minus 38,000. And so we'd be looking at 175,722,000. And that would be the final answer. Now, again, this is more of a challenge type problem, but it's a pretty good way of kind of synthesizing the solutions. And I think it's more like a kind of a group sort of problem, discussion problem. It's an okay to fail type of problem. You know, like try this problem, see what you come up with. Let's talk about it. And you know, like when you reveal the final solution, even if and maybe you don't even reveal it, maybe it's something you kind of leave hanging. You kind of have your class is all the better for it. All right. So number 4, how many different kinds of pizza can be made if there are 5 toppings from which to choose? So that's kind of an extension to the same idea. And it all depends on the approach that you want to take. But if you're choosing from the 5 available toppings, you got to kind of operate under the assumption that there's a lot of different ways that this could play out. You know, if you choose only one topping. Choose 2 toppings. And so I'm just going to do a copy paste a bunch of times. The only stops making sense after a while. And it's definitely not going to make sense after this one. So choose, I'm going to change this to all 5 toppings. All right. So when you think about the different ways in which you can choose your toppings, there's a lot of conversations that could happen here. And I'll tell you that this concept even kind of is something that the older students even struggle with. It's interesting in that regard because it's relatable because we've all ordered pizzas before, but it's also kind of like what you know, like what are you really after here, you know? So the first thing you have to consider is, does it matter what the order is when people make selections from the different toppings, right? Sometimes coming up with a fictitious set of toppings is a good thing. You know, the 5 possible toppings that are available. You got, I'm just going to move this down. You just make them up, you know, like what are the 5 toppings? We got anchovies. I never had pizza with anchovies on it. I feel like it's wasting my pizza experience. Same thing with ham and pineapples. The ham's all right, but the pineapple I'm not too big on. Mushrooms and or just choosing something with a different letter. Let's say clams. You know, the old Frank Pepe white clams. You know, so you get these different possible toppings that you can work with, and also I think it's kind of a good thing when you start getting into conversations that students can relate to, because now Now the class is taken over with discussions on pizza. Well, I like the pizza at this place. I like the pizza at that place. And I'm like, you know what? Yeah, I'll add it to the list. I'll give it a shot. You know, so if you're choosing only one of the toppings, then it could be any of these, right? So I'm just going to kind of smidge this over and call this an or. Right now, it starts getting more complicated when you're in that gray area in between. So because if you're only choosing one, it's either going to be the anchovies or the ham or the pineapple or the mushrooms or the clams. If you're choosing all five of them, then it's going to be the set of all five of those, right? So this is one outcome. Now, I never worked in a pizzeria, so one of my life's big regrets. But then again, I knew people who worked in ice cream, like they worked at Carvel or Baskin Robbins or something like that, and they said that they got sick of ice cream very, very quickly. So maybe it's a good thing that I never worked at a pizzeria, because maybe I would have got sick of pizza. Although it's one of my favorite foods, so I can't imagine that happening. But I don't know the answer to this, but I can't imagine it really mattering too much if you put the anchovies on first and then the ham versus the ham first and the anchovies. Like I don't know. What we're going to assume is that it doesn't matter in which order you put the toppings on, right? That there are some things that you have to assume when it comes to answering questions like this, right? So when you choose only one topping, this is a total of 5 different outcomes. All right, so I have one outcome where it's all 5 of those toppings on, or I could have the 5 outcomes where I got the ham or the anchovies on one pie, the ham on another pie, the pineapple on another pie, and so on. You kind of look at it and say, well, how many pies can I have under these circumstances? All right. Now, when it comes to choosing 2 toppings, that's when things start getting interesting. Each one of these, I'll star them. Each one of these you could do with your own tree diagram, but it's also the Cartesian pairing, because if you look at this and say, and it would get kind of out of hand, but if you look at it and look at that table that I did for the alphabet, down the vertical column, it would be AHPMC, and along that outside horizontal row, it'd be AHPMC. And then you look at the different pairings that you can have, right? So that's what we're going to do here. We're going to say, oh, you could have, well, can you have anchovies and anchovies? Yeah, double anchovies. Why not? Right. Another possible pairing would be that you could have anchovies and ham, anchovies and pineapple, anchovies and mushrooms, anchovies and clams. But then you got to do the same thing again, starting with ham. You could have ham and anchovies, but then you realize, wait a minute, I already got that one, because it doesn't matter what order I put them in. Right. So it starts getting a little kooky now. Right. So this is a repeat. I already got that one. All right. Ham and ham, double ham, nothing wrong with that. Ham and pineapple, the Hawaiian pie. Ham and mushrooms, ham and clams. I don't know if that's going to taste that good, but whatever, we'll go with it. Right. And you got pineapple and anchovies. Well, I've already accounted for that. Pineapple and ham, I've already accounted for that. Pineapple, pineapple, so double pineapple. Pineapple, mushroom, pineapple, and clams. It could actually be all right, now that I think about it. All right. That as you kind of work your way through this, you start realizing that a lot of these outcomes are getting eliminated. Not a lot of them, but some of them. Right? So then the next one would be, you're starting off with mushrooms. So mushrooms and anchovies, mushrooms and ham, mushrooms and pineapple, all values, all things that have been accounted for already. Double mushrooms, mushrooms and clams. And then the final possible array, row in the array would be clams and anchovies, clams and ham, clams and pineapple, clams and mushrooms, clams and clams. Everyone but the last entry had been accounted for already, right? So this is all associated with two toppings, right? So what you do is you go through and you say, okay, well, how many unique values do I have? I have 1, 2, 3, 4. Oh, that made a square for some reason. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right? So we have a total of 15 outcomes. And I'm going to move this in a sec just so we kind of have it out of the way. You know what it'll do? It'll just kind of shrink it down. I'm actually going to shrink everything down. Oh, I didn't want to screenshot. What are you doing? All right. So we got all those outcomes, a lot of outcomes. All right. Started off with what would have been 25, and then it got restricted based off of the repetition. Right. So then you kind of look at it and say, well, what if the repetition didn't matter? Well, if it didn't matter, then we wouldn't necessarily be talking about toppings on pizza. Right. So there is that component of it. But when you get into ones where you're talking about 3 toppings, you know, you look at it and say, well, this is going to get out of hand pretty quickly. And yeah, it might. You know, that's part of the fun. But the exploration part of it is what makes it interesting. And you can see here that, you know, the first instinct would be, right, well, we got 5 outcomes. This is 5 squared minus the repeats. So the next one is going to be 5 to the 3rd, maybe, minus repeats. You know, so we kind of look at it that way and see what's going on. You know, you make a conjecture, you make a, you know, I suspect that this is how it's going to play out. But we look into it and we see, right? So it could be the trio of anchovies, ham, and pineapple. Right? Maybe it's anchovies, ham, and mushrooms. Anchovies, ham, and clams. All right. It's actually kind of smaller set than you might realize. So, you know, that conjecture it's a thought, but maybe it's going to be an overestimate. We'll see. All right. So again, we want to avoid repeats. So we just got to be careful. So I started off with the A and I said, okay, well, I'm going to take the next 2 along the way and see where that takes me. So I did A, then H, but now I'm going to go A with a P. All right. It is also possible that we could have had, and I kind of neglected this, we could have the double anchovies, we could have the double ham, we could have all those different possibilities. All right. So listing out all these outcomes and listing out all these outcomes is going to be kind of an interesting experience, but it's also rewarding, like I said. All right. So when it comes to 4 toppings, we can look at it and say, all right, well, maybe it's all anchovies, quadruple anchovies. That's a whole lot to say. But really, if you think about it that way, isn't that the same as saying that you're just having anchovies? You know, that's the 1 topping. Right? If you have the 4 toppings, then you might say anchovies, ham, pineapple, mushrooms. You might say anchovies, ham, mushrooms, and clams. And then you might move on to some of the other things, but ultimately you come up with the possible outcomes. So, and that's the whole idea, is that you try to make a conjecture out of it. It's not really the point of coming up with a final answer as much as it is that you learn through the experience. All right. So that was page 7. And again, like I said, it's not, I mean, create a list all we want, but that's not the point of it. All right. Oh, just kidding. So page 8. Repeated addition with rational numbers as multiplicands. All right. All that's talking about is multiplying with fractions, but the idea behind it is for us to get a sense of why we're multiplying with fractions. All right. And so once we kind of go down that pathway, things kind of start opening up. All right. So when the size of a set is not a whole number, then the unit fraction using the unit fraction as the main unit leads to an easy process for computing the product. All right. It's a pretty straightforward process. All right. So when we want to write a unit fractions, if I want to, just to oversimplify a term, same denominator, numerator equal to 1. All right, that's an oversimplification, but really what it's saying is you want a single unit of that fraction. All right, that's what's going on there. So the unit fraction associated with 3/5, the unit fraction, would be 1/5. So if I want to write 3/5 as a sum of unit fractions, what I would be saying is I'd have 1/5 plus 1/5 plus 1/5. All right. And that's because 1 plus 1 plus 1 is going to give me a 3. But another way of writing that, because again, multiplication is the shortcut for repeated addition. Another way of writing that would be to say 3 times 1/5. Either way, you're going to get a result of 3/5. All right. So it's a matter of kind of breaking it down. You kind of look at it in lowest terms. You're looking at a fraction in lowest terms, but also you're looking at the building blocks of that fraction. So you kind of look at it this way. If well, the example here, number 2, a measuring cup has a capacity of 3/8 of a liter. How much water will 2 of these cups hold? That's kind of the idea, is that you can use measuring techniques to come up with a result. But I also kind of look at it this way, where I'd say, all right, I need to measure out 3/4 of a cup of water. Instead of measuring 3/4, what I can do instead is just measure 1/4 of a cup 3 times. All right. That typically is most useful when you have, let's say you only have a measuring cup that maxes out at 1 cup, but then you have to do like, I don't know, a cup and a half. right? So you'd say, I got to do a cup and a half of this. So how am I going to do a cup and a half? Well, what I would do is I would take the half a cup and do that 3 times. Or I can do, like the easier way to do it would be a cup and literally a cup and a half. But you could look at it and say, well, I can do it in half cup measurements and go from there. I actually have a measuring cup. I use it for rice. I think it might have come with a rice cooker, but it only measures out in a maximum 3/4 of a cup. At least the markings are 3/4 of a cup. I think I never bothered to check. It might, if I go right up to the brim, if I go flush with the brim, it might be 1 full cup. But when I have to do something like a cup and a half, I'll be like, well, I'm not going to roll the dice and say that that's a 1 cup and I'll just do 1 and a half. I'll just do 2 of those 3/4 cups. And also when I'm transporting the liquid or the rice, if I go flush with it, I might spill. So instead of doing a full cup and a half, I'll do 2 3/4 cup measurements. Okay. So it's kind of along those lines that we have this sort of concept. Right. So when we say a measuring cup has a capacity of 3/4 of a liter, what I can do is I could write this as, 3/8 of a liter. The unit fraction would be 1/8, and I have 3 of those. Now I'd want to know how much water will 2 of these cups hold. Now it's just a simple matter of taking the 3 and multiplying it by 2. So I'd be looking at 2 times 3 is 6 by the 1/8 unit fraction. And then we could simplify from there. Right. Now you could also just double 3/8 and get 6/8. When you double that, it reduces down to 3/4. Either way, but this gets across the idea of the concept of the unit fraction. I bought 3 half gallons of milk today. How many gallons of milk did I buy? Right. So each of these half gallons is a unit fraction. So how many gallons of milk did I get? Well, I could do this a couple of ways. I could say 3 times a half and then convert that into a mixed number, but you run into a lot of trouble with that, especially if you're kind of planning on doing it that way. Then you're told, oh, you're teaching 2nd grade this year, but you still got to teach the same concept. You're like, oh, well, you can't do mixed numbers. In this case, I'd say I have 3 of those 1/2s, so 1/2 plus 1/2 plus 1/2. And I'd say, okay, well, 2 halves make a whole, right? So I got this giving me a result of 1. One plus a half, 1 1/2. So on a couple of levels, and this is 1.5 gallons, we're getting across the idea of unit measures here, which is good, but we're also, and I think more importantly, we're laying the building blocks for the discussions of converting fractions to mixed numbers, improper fractions and mixed numbers, right? So they're developing an intuitive understanding of what a mixed number would be, right? You'd still have to have that conversation of like the 1 plus 1/2 being equivalent to 1 1/2, but I don't think that's too much of a stretch. You just tell them 3 plus a quarter, 3 plus 1/4, 3 and a quarter, with the and being the addition, right? That's all that is. When I say 3 and a quarter, that and is taking on the role of addition. So for number 4, it takes 1 2/3 yards of ribbon to make a bow. How much ribbon is needed for 4 bows? So I'd look at this and I'd say, all right, well, 1 2/3, that's 1 plus 2/3. All right. Now that 1, we're decomposing it, we're going the other way. We're just doing what I just did in reverse. That 1 could be thought of as 1/3 plus 1/3 plus 1/3. And I need to do this for 4 bows. All right, that's all good. because that 2/3, I can hang on to that in its current form, or I could write that as a unit of a sum of unit fractions. I'll create a little bit more spacing here. Red for those keeping score at home. So I'd be saying 1/3 plus 1/3. So this is the sum of unit fractions. So I want to just do this 4 times over. And you look at it and say, well, that's going to get a little out of hand. Well, not really, because what I'd be looking at is how many of these I actually have. I have 1, 2, 3, 4, 5 of these 1/3. So I want to have 4 bows. So what I would do is I would rewrite this as 4 multiplied by the 5 1/3, 5 times 1/3. So then this would become 20 times 1/3. So now I have a multiplication expression, or equation in this case, that would allow me to determine how much ribbon there would be. So now it's just a matter of going back the other way. Now, easier said than done in a lot of cases, but not unmanageable, right? Because I got a whole number set of quantities here. I got 20 of those 1/3. Now, one way to handle that would be to actually, this wouldn't be the most fun thing in the world, but I could write out that 20, I'm sorry, that 1/3 20 times. It doesn't seem like too much fun, but it is doable. And actually, I'm going to do that this one time just to show you, because it's a matter of collecting groups of 3, right? So I have 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3. That's 5. Oh, a little off the mark there. Move this over a little bit. $20 of those 1/3. And so I'd be looking at this by saying, okay, every grouping of 3 of them gives me a whole unit. So there's one group of 3. There's another. I'll leave that one off at the end because it doesn't have a natural partner. Another group of 3. So I have 6 groups of 3, and then I have a couple of straggler 1/3s off at the end. So those straggler 1/3s can be combined. 1/3 plus 1/3 is 2/3. Get rid of that side of the room. And so I have 6 whole number values and 2/3. And so that would be specifically in yards. Now you could, like I said, do it other ways, but the point behind all this stuff is not for you to show me how wonderful you are at multiplying fractions. It's can you use the concept of unit fractions to come up with a solution? So on the skills assessment, I mean that's the only thing when people get jammed up, they get something wrong. It's almost never because they don't know. It's not because they don't know how to multiply. It's because they lost track of the way that the question is really asking them to do it. Right. So you just got to be mindful that there are requirements in how you're supposed to come up with these solutions. And if you don't follow those requirements, then you're gonna pay a hefty price. But yeah. So there's a little learning curve involved here, but it's not anything too terrible. You just gotta expect it. It's something that you're going to be expected to do on an assessment. So, so yeah. Anyway, what I wanted to do now, because I want to give you a the gift of time, is I wanted to give you a quick breakdown of the tech assignment. All right, so I'm going to stop this recording.